How's it going, guys? Weekend? Everyone's like moving this side of the room. All right, so how's it going? What do we got? Questions? Homework questions? Anyone? Yeah.
So for number 28, it asks for the spanning tree of the network, but it's like already a tree, so I'm
Okay, yeah, I actually was silly and I didn't bring my book down. Does anyone have a book that I could look at the problem? You have it?
Yeah.
Okay. Yeah, if it's already a tree, the spanning tree is only one possibility. So, yeah, that's a fair answer. Yeah, good. Other questions? Everyone's happy? So yeah, I didn't tried not to ask too many questions. I'm sorry. I'll put a new homework up today for due next week, and you should have the last homework graded by tonight or tomorrow. So updated. Okay, well, if there's no questions, yeah, go ahead. Yeah.
Is it online? Is it taken in class?
Well, I don't like online exams, and in my view, I mean, sometimes you need to use them, right? I mean, I've had like this experience recently where there's not many options. So for me, the choice is really between like a take-home exam and in-class exam. And I haven't completely decided, to be honest. Only thing I worry about with take-homes, I mean, I do want, I'm not very good at this, but I'd love it if people were more involved with the material. And I really worry about people falling off and just not learning anything or enjoying any of it. So I like some kind of classroom engagement, but I also understand, you guys don't love this stuff too much. And so I don't want you to like, it's less important to me that you walk out of here like remembering all these concepts than having been exposed to some of them. Okay, so anyway, we'll see. I will let me give myself a deadline and I'll tell you the answer to that question Wednesday. That's I don't remind you. Any other questions? Okay, guys. Well, in that case, let's push forward. So we're moving into I believe chapter 8, which is about scheduling. So, I mean, I will say, having read and written a lot of math in my life, you know, I know people don't have the experience, especially like people out of high school or when they take math classes in high school and middle school. I don't think there's any familiarity with actually reading math books. How many people would agree with that? Okay, you disagree. People, you guys like read math books? When you like, if you get your math book in school, you've actually like read through it. No. I mean, I think the common experience is you look at the problems when it's time for homework and you do those problems. And if you have a lot of trouble, maybe you flip back and look at an example or go online or something. Okay, that's the common experience. However, I really recommend reading this book, not because it's a great, beautiful book, but because you will actually learn and it's not hard. It's not a hard math book. There's a lot of words in it. And so you can kind of like read it without a lot of, you know, feeling like you're bogged down in technicalities. So I really recommend it. I think you'll get more out of, you know, you'll be more prepared for any kind of quiz or, well, any kind of test, homework. If you do that. So I would recommend it. It's very, very casual. All right. So I did that. I read through this. Some of the previous chapters I've skimmed, but I actually had to read this one because scheduling is not something I know anything about. But I understand now how they make the models. They have some vocab that they set up. We're going to talk about it. So one thing they have, the idea is they want to schedule some kind of set of tasks and who is actually accomplishing the tasks or what is accomplishing the tasks. These are called processors. These are whatever is accomplishing tasks. And they label them P1, P2. So the processors could be like, you know, chefs in a kitchen, making, you know, the task is to cook some orders. They could be painters in a house. The tasks are to paint the house. It could be microchips in a computer, and the task is to, you know, run a computer program. I mean, whatever it is, it's just some collection of things that can accomplish whatever tasks are sent their way in whatever job you're talking. Okay, so we have processors. And they have these things called, then they have the tasks themselves. And they go through, they say these tasks are in 4 states. I think that's just like a lot of words. I'm not sure. I mean, reading through it, I didn't see these words really used significantly. So let me just verbally say them. So they're okay. Well, all right. So they're states, but I don't want to overemphasize this. I'm not going to just remember all of this. So there's like the ineligible states. There's a ready states. Our state can be ready, be in execution, or it can be complete. So it's just saying, okay, I don't know, like some states you can't actually, some tasks you can't actually do those tasks because you haven't done something that would allow you to do. So they're ineligible. Right? You're painting a house. You can't start painting the house if you don't have paint. So maybe the first task is to get. But you can say that actual painting is a task and it's just ineligible at a particular time. And then you have states that are ready to be performed, or tasks that are ready to be performed. And then you have tasks that you're actually performing, and then you have tasks you finish. So pretty self-explanatory, I'd say, but yeah, don't worry too much about that language, I don't think. But a big ingredient here for this theory that they set up is the processing time. And it's just, I mean, it is what it says it is. It's the time it takes processor to complete a particular task. So these processing times are set to tasks. I don't know if it makes sense to anybody, then just tell me if you have a question. Give a task. So this is task dependent. In other words, it's not about the processor, it's about the task. Processing time is how long it takes to complete the task. Any processor will take the same time. Given task. So some of this theory is not particularly, it's not completely accurate unless you're looking at like computers, because oftentimes different, even then, but oftentimes it would be processor dependent, but whatever. And then again, one of the key things we have is this notion of a precedence relation. So this just is something that tells us which tasks have to be completed before other tasks. So given two tasks, you have a relation, precedence relations, if one task has to be completed in order for the other one to be completed. Make sense? So task X precedes task Y if X must be completed. Y can be. I guess we'll use the language ready. These are the four key things to kind of input into the model for inputs. Questions? So they talk like in the book about, this being like really dry and boring and dehumanizing and all of this, right? Whatever, I don't know. It's life, right? Maybe it is dry. I don't know. I don't know. It seems very applicable to many different situations when you start thinking about all the applications. But whatever. So now, okay, so in any mathematical theory or any model you kind of set up, you have sort of inputs and then you have assumptions that you have to put on. If you don't really clarify those things, right, then you're really kind of lying to yourself, right, and to whoever you're talking to. So, I mean, the whole point is that, like this, whenever you're an advertisement, they say it's scientifically tested or whatever. You have to be very skeptical. Like models are only models, right? They're always idealized versions of whatever is happening. I mean, unless you have a very basic situation. So you need to know what assumptions you're putting into your model. This is the data that's coming in, but what are we assuming about this data? So what are our assumptions? Well, they actually use different words for these. They have three main assumptions. So one is they assume this, they call it versatile or versatility. That has a particular meaning, which says that any processor can complete any task. Again, that is not in many, many different jobs that you might have where you have a team working on it. That's never true, right? Like you have team members that do special things, right? They don't, goalie doesn't go and become some other, play some other position all of a sudden at an equally good level. So that's kind of silly, but it is an assumption. In some models, you would have this. Some situations you have. Second is uniformity, which is again sort of a processor assumption. And it just says that any process or processing time is the same for any process. So of any given task. Not at all depends on, doesn't at all depend on the process. And then the third assumption is persistence. Which just says that any once a task starts, it will continue until it's finished. So you don't stop it and do another task and then come back to it. It's also not the way things work in general. If you have homework and you have several tasks being several different homeworks, and you're thinking about scheduling them, you may start on one assignment, do half of it, do some other, and get back to that assignment. That would not fit this model. This would say you need to finish each assignment before moving on to the next one. Make sense? So these are the assumptions they have. Okay. What we want to do, and this is it, guys. This is all the vocab and the setup for our scheduling problem. So now the goal is, let's say we have a situation like this. We want to actually schedule the timing of these tasks to the different processes. And of course, what we would like to do is do this in such a way that it is efficient, right? Maybe do it as quickly as possible. That's the sort of end all goal, is to find some optimally fast scheduling for models like this. So before we get there though, or before we start really getting into it with that, I want to talk a little more about this precedence relations. About chicken noodle soup. Okay. Good. I'm sorry for what? Yeah, I mean, vegetarians, it's okay. You can replace like a tofu or whatever. I don't know about tofu noodle soup. That sounds awful. I'm not sure there's much I mean, you could make a lentil soup, and then replace the noodles with like chard or something. Something like that. What are you saying? Noodles out of vegetables? You make veggie. It's hard to, yeah. I'm just talking about the chicken part.
Oh.
Yeah. There's like all these meats that are kind of not, I don't know about chicken, like the fake meats. Sounds really bad in the soup. I wouldn't do that. If you want, you can tell me. My vegetarians in the audience. We can talk about vegetarian soups, but I'm just not, it's not my thing. So I want, this is an illustration of how not to make it. I mean, I don't want you guys to like be adults and not know some basics of how to cook. That's horrible. But really, like, of understanding precedence relations and how we model. So I give a lot of tasks in this, probably too many. I think I listed them last time. So I'll relist them here. Okay, so so this is kind of the way the book also uses their notation. Because they'll use a letter or maybe a couple of letters for the tasks. And then they will interpret them, and then these are the letters that they use when they put in the schedule, scheduling. So I'm gonna explain how to do this. After like kind of looking at this though, I have to say, I'll make a couple of columns here. It would be really cool to like, you know, see recipes written this way. Don't mind it so much. Okay, so this is all the A's are add. And then these are, so we want to add carrots, celery. So what is this, by the way? Everybody knows this? Does anyone cook? Anyone, any chefs, aspiring chefs? No? Oh, good. Well, what to say to that? I mean, okay, so if you're cooking in a restaurant, so this is cooked chicken, I get it. I really have, oh, I don't know why I did this. Okay, yeah. Should just put this in with prep. Okay, we'll do this diced chicken. If you're cooking, I mean, cooking in restaurants is awful. I mean, depending on where you are. If you're a chef, then maybe. But it's a lot of work and it's hot, miserable. Cut yourself and add butter twice. Add broth. Okay. So good. And P is just prep veggies. Okay. So these are all of the tasks. I mean, I'm like leaving off, you know, turning on burners and all of that stuff. These are all the tasks I would say that if you want to make a very basic soup, you need. But now, our aspiring chef here, tell us what, and this is not, there's not one answer here, what to do first. Pick one. So should we add? Sorry. Should we add chicken? Before we cook chicken? Yeah? Cook the chicken. Yeah. Salmonella is like, I mean, it's okay. You can do it, but you have to be like kind of very good about really cooking. I mean, most good, I would say you want to cook it first, depending on how you want to do it. But I usually cook and then dice. But really, before you do that, I mean, you can cook chicken. So actually, this is true. So we can cook chicken. Oh, shoot, I'm running out of it. So let's get this. So what I want to do, here's what the goal is here. We're going to make a recipe. We're going to make a recipe in terms of our models here. Talking about the precedence relations. The precedence relations come in as a way of, in a sense, making, it doesn't solve the scheduling problem for us, but it does sort of make a recipe. And then you have to decide how you want to cook it. So what we can do is we can cook the chicken first. That's okay. And go out on the grill. You can also do a shredded chicken if you wanted. You can do that, whatever you want. Cook the chicken. And we're going to prep noodles first. You don't have to. You can wait a little while. But you don't need to do something before you prep the noodles. It's nothing that has to occur before that. There's nothing that really has to happen before you prep the veggies. Except you have to get some knife skills. You don't cut yourself. You can dice them, do all that, cut up your garlic, all. These are things you can do all. Now you can't, you shouldn't, you could. Actually, you could, and if you're making like a stir fry, it's fine. But you should, I think in chicken soup land, it's better to cook the chicken first and then dice. So we'll dice the chicken after. And this is the key kind of ingredient in these graphs, these recipes is if we have a precedence relation, the way we're going to represent this, and we'll talk more about this in a second, is with an arc. They call it arcs, but it's an edge in a graph, a directed edge from one to the other. Initial vertex or point or node is going to be the thing that has to occur before the terminal vertex. So you can do all of these things pretty much independently. But then what you need to do, you need to turn on the oven, right? And you need to add butter. And this, our aspiring chef and all of you guys should know. Because you're going to make a mirepoix, right? You're going to make your mirepoix. You guys know? Nobody, you said you know, someone says they know how to cook, but they don't like it. Okay. You're making a soup, you have to make a mirepoix. It's a requirement. It's like French, first thing you make. And what do? You melt butter, or you can use oil. You don't have to use butter if you don't like it. After you add butter, melt it. You don't want to, like, you're not sauteing these things, right? You're just going to get their flavor, sweeten them up a little bit. You add your onions, add your carrots, add your celery. If you throw those guys in to a big piping hot thing of broth, you guys are officially banned from ever feeding any other person food. That's the worst thing you can ever do. Do not do that. It's not the worst thing you could ever do. I mean, there's probably some worse thing, but that is awful. Like you're, taking human beings thousands of years to learn how to make good food. So you want to cook your vegetables first. Cook them down a little bit. Okay. Once you have that, you don't throw in that mirepoix is garlic. Okay. You burn that garlic. Don't give it a little time, then put it in. So after that, garlic. You can add the garlic, but just add a little. Right? Now you wait a few minutes. Each of these has a certain amount of time. And I would even say if you're making a mirepoix, I think onions and carrots are first. I think celery makes it a little bitter if you do it too much. So the processing time, we're getting the language here, of each of these tasks is a little bit different. Okay, once we're here, now it's kind of a little loose. I mean, you can do a kind, you can add butter, or sorry, add broth if you want. You can add the chicken. But I guess I should say, if I'm going to add chicken, I should probably have cooked it and diced it. So that means I need another one of these relations here. Okay. Oops. I can add broth. You cook it down a little bit. And only after it's sort of cooked nice and warm, only then you can add your noodles. You don't want to add your noodles right away, right? Because then they get all soggy and disgusting. Nobody likes that. Right after you add the noodles, to serve. A little parsley if you want. Salt, pepper. I missed this. These guys you do all the time. So these vertices, these nodes, are independent and they're all over the place. Should always be seasoning, tasting. Right, always seasoning, tasting. Adjust the season. This is dumps. Adjust it, tweak it. That's a nice recipe. I like that recipe. What do you think? Well, this will be on the test. I mean, not this. So my wife tried to talk me out of doing this. Was she right? Was it okay? Do you guys feel bad? You learned something? Your fault? No comments? I mean, does everyone understand the idea behind the precedence relations and how they're depicted though now? Like with the graph? Okay, we're going to talk more about it. All right. So the one thing that's missing in this graph from the four things we have, well, there's actually a couple of things missing, or maybe implicit. So if I look at that recipe and I look back at what we started with these four concepts. So how are these represented in this recipe? Well, the processors, I'm going to assume there's just one processor and it's whoever's cooking the soup. There's just one processor. We could make two if we wanted. We could say two people are cooking together, whatever. The tasks are each of these nodes. These are the tasks. Each of these are tasks. I did not put in the processing time, as I said, of each of these. But if I wanted to, I could do that. So we could say, okay, well, to prep noodles, I mean, altogether, it depends if you're talking about also boiling the water but whatever, we'll say like, 10 minutes, you've got a very fast range. Boil water and put the noodles in. You actually, for chicken noodle soup, you don't really need like al dente because it's going to cook when you put it in the soup. So, anyway. But this is how they would denote that this task takes 10 minutes. I'll put it in parentheses. And they'll do that with each of the tasks. And that will be the processing time of each task. Okay. And then, well, the precedence relations are these areas. So we do see that. All right. So given one of these setups, this and a schedule, which gives us an order in which to do things. We say finishing time is exactly what you think it is. It's just the time to complete the job, time to complete all tasks, total time. Complete all tasks. Now I'm going to give a less complicated example. And maybe one that's more familiar. Okay, so here's the example I want to look at. So you're partnered with another student. So I don't know, I'll just say two students. I won't make it personal. Two students are paired together of equal intelligence and equal skill. To work on a project. Let's say a paper. Okay, they have to write 2 chapters, an introduction and a bibliography. That's the structure of the paper. It's an introduction. It needs 2 chapters, so chapter 1 and chapter 2. Maybe we can call them sections. I don't know, chapter might be a little big. I'll say chapter 1, chapter 2. And a bibliography. So I'll call this chapter 1. I'll use a subscript here, chapter 2, and B. Okay. Now, they don't know exactly, so they're going to divide up the work. Okay, one student's going to take a few of these, and the other's going to take the other. Yeah. They don't know exactly what all the references they're going to use in the paper, so they need to wait until at least the chapters are done to make the bibliography. The bibliography must be made after the chapters. Now, the intro, they're just going to wing it and write whatever they want, whoever writes. So when I wrote that down, bibliography must be made after the chapters. What did I do? What did I impose on this model? Some constraint. It will affect the finishing time of this thing. That's true. But there's this other word. It's kind of like adding chicken before cooking. Yeah. Precedence relations. Right. We have something has to proceed. Doing the chapters, finishing the chapters must precede creating the bibliography. And we can represent that in terms of these arrows that I used. So we can represent this by a simple what we're going to see is called a directed graph in a minute, where we just this. So we don't have any constraint on this I, so I'll just write that over here. Now I'm going to add in the processing times into this. So we're going to say that the introduction will take 3 hours. So the time, processing time, call it P time. 3 hours. The first chapter is going to take 5 hours. And the second chapter is going to take 6 hours. And the bibliography will take 2 hours. Let me Okay. So now the goal is to schedule it, is to decide who's going to do what task and what in what order. Okay. That's at the end of the day, that's what we want to do. That's what this is all about. So let's do it. I'm going to copy this because I want to give a couple of different examples of scheduling. And let me bring this down here. So this, everything that's now on this page here, once we understand the problem, we've sort of coded that problem, and everything that we need to know about it is diagrammatically written here. The times are written in the parentheses, and the precedence relations are written here. And now the problem that needs to be solved is a purely mathematical problem. Let's do that problem. Okay, so our first try, I'm going to just say that P1 is the first student, P2 is the second student. So the first try, I'm going to say that, well, the first student wants to write the introduction and chapter 1. They're first, they want to do the first things first. They say, okay, I'm going to do the first things first and you do the second thing second. I'll do the first bit. You call me when, or I'll call you when I'm done. You get to work on it. Well, or they'll put this in their schedule. So I can smooth it. Okay. And so now, second person is tasked with the second chapter, so they get started right away. But now, can I do this? Is it okay? Everyone's happy? This looks pretty optimal to me. Right? Yes?
So with the time of the work on there, does it matter? Like, if since it like says you know how to line up with the chapter words. Finished, or does it not matter? It's just talking about the times.
Are you saying, I'm not sure I understand the question. So explain again to me.
So, okay, so the chart in this says chapter 1.
Mhm.
And it goes to 8 out.
Here.
Yeah.
Yeah.
With that, do you have to move after that is done?
Good. This is a schedule. It is a schedule, but it's not a valid schedule. It's not one that actually follows our precedence relations. Our precedence relations say that you can't start on the bibliography until both chapters are finished. So right here, this chapter has not been finished yet. And so you cannot do that. Good. Very good observation. So I do need indeed to kind not to do that. I do need to move this until after this first chapter is finished. And usually what the book puts in here is they'll write in idle here. And maybe idle up here. So for this schedule, we have a 10-hour. It's a valid schedule, but it's going to take total, the finishing time is 10 hours for this schedule. So is this the best we can do? Is a question. The answer is no. You want to suggest anything else? Is there something different I could have done? That's right. So I could have done something very similar. In fact, the people could have taken the same tasks. First student could have taken chapter 1 in the introduction, but instead of, actually, this is a common practice when I write papers with my colleagues. We almost always write the introduction last. We get to work. We're going to write the chapters. We're going to write the sections, prove the theorems. Then at the end, we'll go back and say, this is what it's all about. We write the introduction last. Very sensible. Not the way you want to read it, but it's the way you want to write it. And if you do it this way, then indeed, now student 2 can call student 1 and say, send chapter 1 over to me. I'm done with chapter 2, and make up the bibliography. And we do have a valid optimal schedule here. Valid. And the finishing time is 8 hours. If there's no idle time at all in your schedule, then it's going to be optimal. And some schedules, some setups like this, some problems like this, you have to have some idle time. It's not do it this way. Questions about this? This is it. I mean, this is as hard as it gets. Like these are all of the ingredients are working together here. Now what we're going to do is try to figure out how to come up with these optimal schedules by using some math. Okay. So to do that, we need to introduce a variant of something that we've been playing with for the last couple of weeks, 2.5 weeks. And that's the notion of a directed graph. Directed graphs. We've already seen a couple of them. Our chicken soup recipe is we wrote as a directed graph. So these are also called digraphs. But whatever. And unfortunately, so I'll be honest with you, mathematicians don't do this. Mathematicians call they do call directed graphs, but we usually call edges of a graph edges. We can call them oriented edges or directed edges, but we don't call them arcs. But probably people that are using these in models do call them that. So if you ever experience this in the real world, you may want to know the language. This is in applied mathematics, this is like rampant, where you get a certain language that mathematicians use, and then applied people use other language. They just, because they're creating their models and not so concerned with the language we use. But so for a directed graph, an edge is called an arc, and it's not exactly the same thing as an edge because it has a special initial point and a terminal point. Edges in graphs, they don't have any preferred direction. They can be either way. But in a directed graph, you have initial and terminal. So they're usually diagrammatically written as an arrow. And that edge is different than the arrow pointing in the opposite direction. Those are two different, looked at mathematically as different. So we would write this, if you were to write it without the arrow, you would just write it as x, y. Here we have the initial point, and here we have the terminal or node. Vertices are called nodes often. Just put the new language here, sorry. Nodes or vertices. No difference there. There are two other things that are slightly different. One is a path. Path can no longer be just a sequence of edges starting at one vertex and ending at another. These paths for directed graphs, you need to be following the direction of the graph. You can't go against the direction of the arc. Okay. So this is a directed of arcs. I'm just going to leave it at that, but you know, pictorially, I'll just grab this picture. So you get a picture like that. And then the final kind of difference here, or more subtle thing you have, is you have an out degree and in degree. So instead of just having a degree of a vertex, I have a vertex X and I have a situation like this. Sorry, I'll just finish this up in 1 second. Then here my out degree is 3 of X and my in degree is 2. So I have 2 arcs coming in, 3 arcs going out. So the total degree is 5 still, but you can kind of partition that into 2 sets. This is out degree is 3 here. All right, guys, we'll continue on Wednesday. See you then.